this problem gives us the pH of a calcium hydroxide solution and wants us to figure out what the molarity of that solution must be. So there's a couple of different ways you can tackle this problem, and I'll show you both ways. It doesn't matter which way you do it. It's whatever your brain thinks of first, whichever way your brain likes better. It's up to you. So here's an example where you will see why chemists even came up with the CaOH idea. It really is just a mathematical shortcut. Sometimes when you're working with a base, it's actually more mathematically convenient to use the CaOH value instead of the pH value, as you'll see. So calcium hydroxide is CaOH2. If we have an aqueous solution of calcium hydroxide, it would break up into 1 calcium ion and 2 hydroxide ions. So we're going to treat calcium hydroxide as if it were a strong base. Now, if you're a smarty pants out there on the internet and you are looking up weak acids and bases, strong acids and bases, it will not list calcium hydroxide as a strong base. I'm just using this guy as an example. So we're going to pretend that it is a strong base and breaks up 100%. So it gives us the pH is 11.4, but because I'm working with a base, I'm going to try and find the pOH. And I know that the pH and pOH always have to add. So if I subtract my pH of 11.4 from 14, I would get 2.6. Well, the 2.6 is the power of my hydroxide concentration. So I would know what my OH minus is going to be. It would be 1 times 10 to the negative 2.6. And because I'm working with a base, there's your hydroxide. A little more convenient, right? So that's what we want, but it's not a properly written number. If you throw that into your calculator, you will get a properly written number of approximately 0.002512 molar. Or it might be written as 2.512 times 10 to the negative 3rd molar. So this guy wanted us, that's the molarity of the ion, but this wanted the molarity of the whole chemical. So I'm close, right? That molarity to 0.002512, capital M stands for moles of hydroxide per liter. And from my balanced equation up above, it says that there are 2 hydroxides for every 1 calcium hydroxide. Therefore, the molarity of the whole chemical is going to be half that of the ion. And so we'd get a molarity of about 0.001256 molar calcium hydroxide. Again, sig figs being what they are in this chapter, it just gets messy when you have exponents and logs and things like that. So as long as you have an answer anywhere close to that, I would accept it. So on a test, you'd say something like 0.0013. That sounds great. 0.00126. That sounds great. Just make sure you don't chop it too much. It's actually better to write down a few extra numbers than not enough. So I told you that there were 2 different ways to solve this one. So this is path number 1, where you go from pH to pOH. Another path that you could take is if you know the pH, you know the power of your hydrogen concentration. So I could do 1 times 10 to the negative 11.4. Throw that in your calculator to convert it into a proper number for you, and it'll give you roughly 3.98 times 10 to the negative 12 molar H+. Well, if we know the H plus and we need the OH minus so we could get the molarity of the whole calcium hydroxide, we know the equation that if you do 1 times 10 to the negative 14th over the 3.98 times 10 to the negative 12th, that'll give you the molarity of just the hydroxide ion, which would give you an answer of 0.002512 molar. This should sound familiar, right? And from that point forward, you jump right back into the same thing we did here.